Improper integrals. There are two types of improper integrals. One, where the interval of the definite integral is infinite. One or both limits of integration are infinity. Or two, if f has an infinite discontinuity, a vertical asymptote. But there would be a finite number of infinite discontinuities. So for an infinite integral, if f is continuous on the interval a to infinity, then the integral from a to infinity, what makes this improper is the upper bound is infinity. So I take the limit as b approaches infinity of the integral from a to b of f of x dx. 2, if f is continuous on the interval negative infinity to b, this negative infinity makes it improper. So I take a limit as a approaches negative infinity of the integral from a to b of f of x dx. If f is continuous on all real numbers, then the integral from negative infinity to infinity is equal to the limit as a approaches negative infinity of the integral from a, I break it up at some value c, plus the limit as b approaches infinity from that value to the upper bound b. So an improper integral is called convergent if the limit is a real number, meaning that the limit exists. Otherwise, it is called divergent if it goes to positive infinity or negative infinity, or if it does not exist. So evaluate the following integrals. The integral from 1 to infinity of 1 over x dx. So limit as b approaches infinity of the integral from 1 to b of 1 over x dx, which is the limit as b approaches infinity of the natural log absolute value of x from 1 and b. If I plug in the upper bound, so limit as b approaches infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0, so I get the limit as b approaches infinity of the natural log of b, which is infinity. So this integral diverges to infinity. If I take a similar integral, but instead of 1 over x, 1 over x squared dx. So it's an improper integral since the upper bound is infinity. So limit as b approaches infinity of the integral from 1 to b. To integrate 1 over x squared, I'm going to bring it up as a negative exponent. So this is equal to the limit as b approaches infinity of negative x to the negative 1, evaluate it at 1 and b, which is the limit as b approaches infinity of negative 1 over b minus a negative 1 over 1. So 0 plus 1 or 1. So this integral converges to 1. So if I compare these two, for what values of p does the integral from 1 to infinity of 1 over x to the p converge? 1 over x to the p dx converge. 1 is the cutoff. So if p is less than or equal to 1, then this integral diverges. If p is bigger than 1, then this integral will converge. So evaluate the integral from negative infinity to 0 of x e to the x dx. So this is improper, which means I'm going to write this as the limit as a approaches negative infinity of the integral from a to 0 of x e to the x dx. So I'm going to integrate this using tabular integration. I'll make a column for x, a column for e to the x. If I differentiate the left side, and if I integrate the right side, and then multiply on an angle and alternate the signs. First sign's a plus, that sign's a minus. So this is equal to the limit as a approaches negative infinity of x e to the x minus e to the x evaluated at a and 0. So limit as a approaches negative infinity. If I plug in 0, 0 minus e to the 0, which is 1, minus, if I plug in a e to the a minus e to the a. So this is equal to the limit as a approaches negative infinity of negative 1 minus a e to the a plus e to the a. Okay, if I take a limit of the first term, the limit of a constant is the constant itself. The limit of this term is going to be 0, since e to the negative infinity is 1 over e to a large number. So I have negative 1 minus the limit as a approaches negative infinity of a e to the a. So this limit is negative infinity times e to the negative infinity, which is negative infinity over infinity. So I'm going to have to use L'Hopital's rule on that limit. So I can write this as negative 1 minus the limit as a approaches positive infinity of negative a divided by e to the a. So now if I use L'Hopital's rule, negative 1 minus the limit as a approaches infinity of negative 1 divided by e to the a. Now if I take a limit, negative 1 minus 0, which is negative 1. So that integral converges to -1. The integral from 0 to infinity of e to the x over 1 plus e to the x dx. So if I write this as the limit of b approaches infinity of the integral from 0 to b of e to the x divided by 1 plus e to the x dx. So this is a u substitution. If u equals the denominator, 1 plus e to the x, du is e to the x dx. So the integral will turn into du divided by u, which is natural log of absolute value of u. So natural log absolute value of u plus c. So this is equal to the limit as b approaches infinity of the natural log. I'll drop the absolute value since 1 plus e to the x is always positive. 0 and b. So the limit as b approaches infinity, if I plug in b, 1 plus e to the b minus natural log of 1 plus e to the 0. So if I take a limit as b approaches infinity, e to the infinity is infinity, plus 1 is still infinity. Natural log of infinity is some sort of infinity. Minus e to the 0 is 1. So natural log of 2. Infinity minus natural log of 2 is equal to infinity, which means that this integral diverges, or the integral is divergent. The integral from 0 to 8 of 3 over root 8 minus x dx. What makes this improper is if I plug in 8 in the denominator of the fraction, I end up with 0. So this is the limit as b approaches 8 from the left side of the integral from 0 to b of 3 over the square root of 8 minus x dx. To integrate this, I'm going to do a u substitution. U equals 8 minus x, so du is negative dx. So the integral turns into 3 dx is negative du. So negative 1 over square root of u, so u to the negative 1/2, and du. So if I integrate this, negative 3, I add 1 to the power, divide by the new power, so multiply by 2 plus c. So this is the limit as b approaches 8 from the left of negative 6 square root of 8 minus x. And evaluate it at 0 and b. So negative 6 square root 8 minus x plus c. So I integrated it off to the side. When I put it back with bounds of integration, I remove the plus c. So if I plug in b, and if I plug in 0, and if I take a limit as b approaches 8 from the left of -6 times the square root of 8 minus b minus the square root of 8 minus 0, which is -6. If I take a limit of the first term, 8 minus 8 is 0, minus the limit of the next term is the constant itself, so minus square root of 8. So this is 6 square root 8. I can break down 8 as 4 times 2. So this limit is 12 root 2, and that integral is 12 root 2, so the integral converges. So this example is an interval with an infinite discontinuity. So if I have a function that has a vertical asymptote at b, so intervals with infinite discontinuities. One, if there's a discontinuity at the upper bound b, then the integral from a to b of f of x dx equals the limit as c approaches b from the left of the integral from a to c of f of x dx. Two, if there's a discontinuity at a, then the integral from a to b of f of x dx is equal to the limit as c approaches a from the right of the integral from c to b of f of x dx and then if there's a discontinuity at c, which is somewhere inside the interval a to b, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, which is the limit as h approaches c from the left of the integral from a to h of f of x dx plus the limit as k approaches c from the right of the integral from k to b of f of x dx. So the integral from 0 to 2 of 1 over root x dx. So what makes it improper is my lower bound is 0. If I plug in 0 into that expression, I get an undefined value. So I'm going to take the limit as a approaches 0 from the right. To integrate this, I'll bring it up to the numerator and make it into a negative exponent. So 1 over root x dx. So first step, rewrite it without the lower bound and introduce a variable. Limit as a approaches 0 from the right of the integral from a to 2 of x to the negative 1/2 dx, which is equal to the limit as a approaches 0 from the right of 2x to the 1/2, evaluated at a and 2. So limit as a approaches 0 from the right of 2 root 2 minus root a. Since a is approaching 0, if I take a limit, this is 2 times root 2 minus the square root of 0 is 0. So this integral converges to 2 root 2. So even though this function is unbounded, it has finite area under the curve. The integral from negative 2 to 0 of 1 over x dx. What makes this improper is that the upper bound is 0. So the limit as b approaches 0 from the left of the integral from negative 2 to b of 1 over x dx. If I integrate, the limit as b approaches 0 from the left of natural log absolute value of x evaluated at negative 2 and b, which is the limit as b approaches 0 from the left of the natural log absolute value of b minus the natural log absolute value of negative 2. If I approach 0 from the left side, so natural log of b, if I approach 0 from the positive side now, since it's in absolute values, the natural log goes down to negative infinity. So negative infinity minus the natural log of 2, which is equal to negative infinity. So this integral is divergent, or this integral diverges. And then if there's an integral, let's say 1 over x from negative 2 to 2, I would have to split it up at 0. Since 0 is where the discontinuity is. So this is helpful while you're going through these improper integrals. The integral from 1 to infinity of dx over x to the p is equal to 1 over p minus 1 if p is greater than 1 and diverges if p is less than or equal to 1. You don't have to memorize these, but it is useful just for an understanding. And then for the integral from 0 to 1 of dx over x to the p, this is equal to 1 over 1 minus p if p is less than 1, and this diverges if p is greater than or equal to 1. But you will always be able to write these in the terms of limits and then evaluate each integral using the techniques that were covered. The integral from 1 to infinity of 1 over cube root of x dx. So limit as b approaches infinity of the integral from 1 to b of 1 over cube root of x dx. To integrate this, I'm going to rewrite it as a negative exponent. So the integral from 1 to b of x to the negative 1/3 dx, which is the limit as b approaches infinity of x to the 2/3 divide by 2/3, so 3/2 x to the 2/3, evaluated at 1 and b. Which is the limit as b approaches infinity of 3/2 times b to the 2/3 minus 1 to the 2/3, or 1. If I take a limit as b approaches infinity, I get 3/2 times infinity minus 1, which is 3/2 times infinity, or just infinity. So this integral diverges. And if you match it with this one, p is 1/3, which is less than 1, therefore it diverges. If I change the bounds of integration, so 0 to 1, of 1 over cube root x dx. This is equal to the limit as c approaches 0 from the right of the integral from c to 1 of 1 over cube root of x dx, which is the limit as c approaches 0 from the right of the integral from c to 1 of x to the negative 1/3 dx. So the limit as c approaches 0 from the right of 3/2 x to the 2/3 evaluated from c to 1. So the limit as c approaches 0 from the right of 3/2 times, if I plug in 1 to the 2/3 is 1 minus c to the 2/3. If I plug in 0 for c, 0 to the 2/3 power is 0. So 3/2 times 1 minus 0, or 3/2. So this integral converges. And this one, p is still 1/3, except the bounds of integration would follow this one, and that's why it converges. It just proves, or it's an example of those two that are listed there.